So last time we defined this weird and abstract concept of a compact set. And it's this idea that it's a set that no matter how you cover it with open sets, you only ever needed finitely many of them. No matter how small these open sets become, no matter how refined and separated from each other, And it is not obvious at all to decide when something is compact or not. For example, many fractals are compact. You may have heard of the Mandelbrot set, and it is not obvious that such a set has this property. You would think that you should be able to cover it with smaller and smaller open sets, open balls, smaller and smaller circles, and make this covering very refined so that you do need infinitely many of them, but that is not the case. So studying compactness is interesting, and today I want to tell you how this connects to many other subjects, especially if you're going to take real analysis. You will find this quite useful. You may not realize it right now, but it is actually fundamental to understand things. Okay, so after we gave this definition, we gave some examples of what it means for a set to be bounded and so on, and we identified two important properties that compact sets have, all of them. Compact sets are always bounded, and this gives you infinitely many easy examples of sets that are not compact. Basically, any unbounded set cannot possibly be compact. For example, in the plane, you can take the left half of the plane or something like that, or just a line, a line through the origin that goes is infinitely long. None of these sets can be compact, right? And the second property, which we had a bit of a harder time proving since it was a bit more abstract, is that compact sets are always closed. And this isn't obvious, and I will admit to you that this proof is, I didn't plan on writing this proof. It ended up being a bit more abstract than I thought, but the proof you can see is correct. So you can double check this. It has some interesting ideas that are useful to understand compactness. Now, I am well aware that I haven't given you an example of something that is indeed compact. These two properties are very important, boundedness and closedness. They are in fact so important that they fully characterize compact sets, at least in the real numbers, in the sense that every set that is both closed and both closed and bounded will also be compact. But proving that will take a little bit of work, and that is the goal of the first part of this lecture. For the second part, I will explain why this is important, why someone would care about compact sets and having this weird definition. Okay, before we prove the main theorem, just to continue and finish up this last idea from last time, I want to show you this lemma. I wrote it last time, we didn't have time to prove it, and it is considerably easier to prove. If you have a compact set, then any closed subset is also compact. Now, if you already know that compact is the same as closed and bounded, then this result is obvious, because something contained in a bounded set must itself be bounded. So if it's also closed, well, then it has to be compact. But of course, we don't know that these two things are the same yet, and we are going to need this as a sort of stepping stone to prove that. So let's focus on this lemma, and we have to do this with the definition since we don't have a good understanding yet of what compact means. Like I said, we don't even have an example of a compact set yet, although I will give you a very simple example, or more or less simple. Okay, so how would you prove this? You have a compact set and a closed set that is contained in it. How do you prove that it is also compact? Using the definition, right? We cannot use anything about closeness or boundedness because we don't know if that implies compact. Okay, so the thing, if we just want to apply the definition, we have to take a covering, right? Okay, so someone is suggesting contradiction. I think there's no need to use contradiction in this case, but that would also work. So my suggestion would be, what are we call? I think we call them Fs, right? Let F be an open cover of the set we want to show is compact, because compact means every open cover contains a finite cover. So let's take any open cover and show that we can select finitely many elements of F that still cover C. And how do we do that? Well, for this we have to use two things. We have to use the fact that C is closed and contained in a compact set K. Okay, so how do we use the compactness of K? If we want to use the compactness of K, we somehow need to find a cover of K because right now that's the only thing we know. I mean, we do know that K is K is closed and bounded, but that will not be at all useful to us. Let me maybe draw a sketch. I mean, there's already a sketch here. So the idea is that we know that if we were to cover K with any amount of open sets, then finitely many of them were enough to cover K. And we need to use this idea to prove that the same is true for C. Now the way I drew it, it seems like I'm already taking a cover of K, but the problem is I don't have one yet. What I have is a cover of C. So how do I transform the cover of C, which is F, into a cover of K to use compactness? Right? So this is being drawn in blue, let's say. Right? So I found a cover of C, and it might be an infinite cover. So how do I extract something using the compactness? And this is actually way simpler than the last lemma. So now this is part of problem set, what is it, 5? I think it's exercise 1. I've already quoted this result in the past, right? So by problem set 5.1, we know that C is closed. That means that the complement is open, right? But notice that if I take F and I add this this open set, then this is a covering, right? It's a cover. It's an open cover of C. But when I add this other this open set, apologies, I don't know why I keep saying closed. When I add this other open set, it's not just covering C, because I'm adding everything that is not inside C, right? So this set must be a cover of K, and it's open. Is an open cover. Okay, now you will argue with me. The complement of C is something huge, right? It's way bigger than K, but it doesn't matter. This is still an open cover of K. So if it covers way more, that's not really my concern. So by using the word so too much, okay, since K is compact, there are, what do you want to call them? B1 all the way to Bn finitely many elements inside this cover, right? And I have to use this cover of K, of course. So one of these might be the complement of C, such that K is still being covered by this finite set, right? Such that K is still being covered by only a finite amount of these BIs. Okay, so that's we've made progress because now we have a bunch of stuff that covers K, and this stuff will also cover C, right? C is contained in K, right? So C is also being covered by these. Now the problem is that the BIs are not a finite subcover of the original cover. They are contained in this cover that I am underlining in blue right now. And that is a cover of K, not of C. But you can probably tell me why this is not a big deal, because we can in fact extract a cover of C. We just have to remove something. So who can tell me how I fix this? What is the open cover? Let me tell you how I want to conclude. Is a finite open cover of C contained in F. I want to get a cover from elements of F, right? Right now I have not just elements of F, but there's this imposter. But that one isn't needed to cover C. So all I have to do is remove it, right? Just take the BI's, right, from I1 all the way to, and I don't like that notation, but I already used it, so whatever. And just remove the thing that we don't want, which is this one. That still must still cover C, because I'm just taking away stuff that is definitely not a part of C. So it is still open. I'm just removing sets, right? So the ones that are left must still be open. It's still finite because it's a subset of the previous finite set. I mean, they're labeled. There are at most n elements, and it covers C. It might obviously not no longer cover K, but it still covers C because all I took away is something that is definitely not. It's disjoint from C, right? There's nothing in C there, and now it is contained in F. And by definition, C is compact. Okay, so this wasn't that bad, right? I just showed that closed subsets of compact sets are also compact. Okay, so let me give you now the first example of a compact set. And that will be closed balls. Closed balls are always compact, but to simplify things a little bit, the closed interval AB is compact. Compact. Does this make sense? Every closed interval is a compact set, and that is the first example of a compact set. Every closed subset of such a set is also compact. So for example, if you take the union of three disjoint closed intervals, that is also compact because it's contained in some bigger interval, right? And they are all, of course, closed. So now if I prove this to you, this example, you have many more examples of compact sets. Does that make sense? Or are there any questions until this point? Okay. Okay, so let's prove, just to practice writing proofs in this more abstract setting, let's prove that this is in fact a compact set. And this will be one of the last times that we use the definition, because right now we are about to sort of crack the code on compactness and learn how to understand. We will gain a deeper understanding of compactness after we do this example. And bear with me. I will tell you why this is important, why this isn't just writing random definitions and random proofs using those definitions. This is actually connected to something deep about the real numbers. Okay, so how do we prove that something is compact? Well, we just did it, right? Let F be an open cover of P, and we want to extract a finite cover from F that still covers this interval. Okay, so the way the textbook proof of this usually goes is you define a set E that consists of all real numbers, which will be real numbers inside the interval. Actually, why don't we just go ahead and write it that way? Define E to be the set of all numbers inside this interval. This set might be empty, right? It doesn't matter right now. It won't be, of course. Is compact for every. Let's just simplify things and say that A is less than B, otherwise this set is always empty, and the empty set is of course compact because you don't need anything to cover the empty set, right? So any open cover, you can just remove the entire cover and it still covers the empty set because you don't need anything to cover the empty set, much less a finite collection of open sets. Okay, and what we want is we are going to say up until X, the first initial segment, first and initial are synonyms. I mean, the initial segment of this interval up until the point X is covered by finitely many elements of the cover, of the original open cover. So what does this mean? There's A, there's B. This is a closed interval. And I want to convince you that this entire interval, when covered with open sets, no matter how small, I only ever needed finitely many of them. Now this property must hold true for some initial segment of A. For example, if I take a small enough x right here, then if x is small enough, close enough to A, then eventually this will be in just one element of this cover. Now, why could this be tricky? Is because the cover can look something like this, right? The cover can have open sets that become smaller and smaller and smaller. And then it isn't obvious that I only needed finitely many of them. Because right now, if I continue doing this drawing, I might even be able to convince you that I need infinitely many of them, right? That I can find an infinite sequence and I cannot neglect any of these elements, any of these open sets. Okay, so here's something that I want to underline in red just to highlight it because I will eventually show you, and with help of either the tutorial or one of the additional exercises, that everything that we're talking about, compactness, completeness, and all the theorems that will follow from this, which will be a big chunk of the foundations for real analysis, are actually the same thing. They're different angles of the same phenomenon, mathematical phenomenon, and the connection between these things is quite deep. And understanding this will give you a much better understanding of what the real numbers are and why they're special in a more mathematical sense. Okay, so the first claim is that E cannot be empty. And who can tell me why? E being non-empty means that there is, in fact, an initial segment that is just covered by finitely many elements of F. And this is easier than it looks. So who can tell me why is E non-empty? Why am I able to take a very small part of this interval that is indeed covered, not just by finitely many, but actually by just one element? Exactly. Okay, so in the chat, people are suggesting if we take x equals a, then the interval a comma x is just a point, the point A. And that point is only can be covered by just one element of this cover, right? Just take the first open set that covers it, and then we're done. Okay, and I have another comment in the chat. Is there a paradox for the upper graph by Zeno? Yes, this is definitely related to Zeno's paradox. And the idea, I mean, this will make more sense when we talk more about sequences and stuff. Um, but yes, it is possible to divide something finite into infinitely many pieces. But in this case, it's important that these pieces are open, because when they're open, I cannot do that anymore. There's no Zeno's paradox when they're open, right? Yeah, that makes sense. Okay. Yes. That's a good observation. Okay, so it's a non-empty set. It's also not hard to see that this set must be bounded because everything in E is inside some interval, right? Also, E is bounded, right? Bounded means inside an interval, and this is literally a subset of A comma B. So it is bounded, thus by, and I'm going to write this in red because I want to highlight the fact that this is the most important thing being used here and why this theorem, this example is not true all the time, right? In a different space, in a different topological space, this will not be true and this will not make sense and closed intervals might not be compact. It is actually not even true that closed and bounded sets are necessarily compact in a different space, right? I mean, okay. Thus, by completeness of the real numbers, any bounded non-empty set has a supremum. There is, and just to be consistent, let me try to use the same letter that the textbook has. This is Royden's textbook, by the way. There is C, a number that acts like the supremum of this set E. Okay, So now one claim that just to not overwhelm you with too much proving and notation and stuff, you can prove using just the definition and elementary properties. You don't have to cite anything special for this. You can prove that C is in fact B, right? I'm not saying this is obvious. I'm not saying that this follows just by writing one line. You need maybe 2 or 3 lines, but it's just from the definition. Apply the definition of supremum, apply the definition of open set, and you can easily prove that C must be this element B, right? And then we're done. Because if C is B, then that means that C has the property, right? C has the property. So from here, AB can be covered by finitely many elements from F or of F. In other words, proving this shows that B is also an element of V. But then we're done because that's what we wanted to show. We wanted to show that this closed interval can be covered by just finitely many elements of the open cover that we had at first. Okay, so we have our first example, and we only skip one detail, which is this claim. Actually, maybe I shouldn't write this as a claim. Notice that, and instead of writing this as a claim, let me say this is an exercise. If you want to understand this better, I do suggest you do this exercise, but there's nothing deep about this last bit of the proof, right? The idea that you're sweeping the interval left to right, making sure that you always preserve this finiteness, that's the main idea of this, and this is just an example, right? It's not that crucial. But now I can tell you why all of this is important, because now I can just prove the following. So this is the first named, I think it's the first named theorem we have in this chapter. Of course, we've mentioned other named theorems. Two people, Heine-Borel. And the theorem says what you might expect. So a set of reals is compact if and only if it is closed and bounded. Why does this matter? Bear with me. Let's prove this, since the proof with all the theory we already covered is actually not that difficult. We already know that the forward implication is true, right? This was done last class. And I called it proposition 1 and proposition 2, conveniently, right? So let's focus on the other implication. How do we show that something that is closed and bounded must be compact? And this is easier than you might think. So let K, should we call it K? Why not? Let K be bounded. Actually, let's call it C, just to be consistent with the lemma. Be bounded, closed and bounded. Oh, and I should mention something important. These results work for Rn, right? They are way more general than just for the real numbers. They work in these Rn multiple coordinates. But the proof that I gave you here doesn't work for Rn because, I mean, it's an interval, right? And we are using the completeness of R. Rn is also complete, but it's complete in a different sense. We can't really take supremum and infima in Rn. So even though many of these definitions are way more general, if you scroll up, and hopefully you don't find this confusing, actually I made a small mistake here. More than a mistake, this is just something that I can generalize, right? We can put Rn in all of these. And that might be a little bit better because we don't use anything about the real numbers. But this example, of course, only makes sense in the real numbers because it's an interval, right? Can you prove that closed balls are compact in Rn? Yes. But the proof has to it works a little bit differently. So from now on, we have to focus on R, as opposed to Rn, but keep in mind that these results are all true for Rn as well, right? It is also true in Rn that compact is the same as closed and bounded. But for the example, we do need this other thing. So let C be a bounded closed set of R. So we know that C is contained in an interval. Or that's what bounded means. It's contained in a ball. So in R, balls are intervals, so it's contained in some A, B. But if we just close this interval, then we get that one, right? But this is a compact set. I just proved to you that this interval is compact, and it contains the closed set C. So by the lemma, this is compact. By the lemma, C is compact because it's a closed subset of a compact set. And notice how boring the proof becomes. Now you might be thinking, did it really take two very brilliant mathematicians to come up with this theorem if the proof is so easy? But of course, this is only the way I presented it, and the original proof of the theorem likely contains all of these juicy details as part of the theorem, right? So the way I presented it, it seems like it's just broken up into pieces, but the theorem itself is not trivial, right? Given out of context. Okay, so here is an overview before we continue with the last subject or last bit of subject, an overview of all this. You might be thinking, what is all this nonsense useful for, right? This definition is just so arbitrary. Open cover, finite open cover. How is this useful? So let me tell you why I think this is important. So in the middle, you have the real numbers that we've spent a good third or more of the course learning about, the real numbers. It's a very interesting space. But you can study this from different perspectives. For example, if you go to some civilization and you teach them about the real numbers and say, well, it's a totally ordered structure in which this and that, and it contains this and that, and there's a countable and it's uncountable, you explain everything there is to know about the order, then this civilization would eventually come up with the completeness, the fact that this space is complete. Completeness in the sense of the order, right? Every bounded non-empty set has a supremum and an infimum. That's what completeness means. And they would call this what did we call it? Principle or theorem? I don't remember. Doesn't matter. I mean, the completeness principle, right? But this is not the only perspective. Maybe other people care more about what you can do with real numbers. We want to add them. We want to treat them as vectors. We want to use them to model finance and stuff. So you would tell them about the algebraic structure. And you would tell them that the real numbers are a field and that this field has this property and that it contains the integers and it contains the rationals and all sorts of things. They would eventually say, well, in the algebra, you can add and multiply. And if you remember what these numbers are, they're basically classes of Cauchy sequences, right? So they would say, they would eventually come up this other civilization. They would say every Cauchy sequence converges, right? That's a different conclusion about the same structure. Now, there's other perspectives, and we didn't go into too much depth, but I did tell you how to abstract this. If someone just worries about the topology of R, the perspective of what is the shape of this space? Well, it looks like a line. You can stretch it. It has no holes, but it contains something that is dense and still countable, and it has this and that. You can tell people about the topology. Then these people would probably conclude that something about compactness, right? And this is the next result that I want to show you. So nested interval theorem. Actually, yeah. Nest, should we call it compact since we already defined the word, right? Okay, so apparently you can study the reals from different perspectives. What I want to convince you of is that all of these theorems are the same. All of these theorems belong to a more general, more abstract, greater and deeper truth about the real numbers. And these are just different perspectives of the same phenomenon. They are describing the same thing that's happening. This would only make sense if you study topology in more generality and you realize that these theorems are equivalent under many different definitions, and they are not equivalent in other spaces. So this is actually something that makes the real numbers quite special. And from these ideas, we will derive a bunch of stuff that you might have heard of if you took 137 or other calculus courses. And this is very important. Derived from this will be the Bolzano-Weierstrass. The theorem we just proved is also derived from this idea. You might be thinking, well, aren't we using completeness to prove this? And you're right. And you can see in red, completeness is a crucial aspect of this. But this is actually just derived from these ideas as well. Heine-Borel. I mean, they're equivalent, right? They're all derived from each other. And let me see, is there anything else that I wanted to derive from this? This is pretty much it. But you will see how these are very useful because they combine different perspectives of the same thing. Okay, so for the next bit of the lecture and the last topic, I will prove some results, tell you how this connects with others, and we will have some extra time to ask questions and discuss the quiz together. So let me pause the recording.